counting down. Hang on. All right, so I should be recording right now. So hopefully I'm like recording my screen, I'm recording my meet, and you can see my camera. So I'm going to post it. If you're just watching in slow motion, just try and listen for right now. If you have no video, we're going to get through this. All right, so proving continuity here. We need those 4 different types of continuity from 1.5, or the 1 type of continuity and the 3 types of discontinuity. Does anybody remember what they were? No. You can't hear me, Alyssa?
No, it broke up. I didn't hear what you said.
Oh, what are the 4 types of continuity? SG mutes. So I'll tell you the first one is continuous. What else was there? What do you call, how do you classify it when there's a hole? No, just me again. Okay, there's removable, infinite, and jump. Okay, so we're going to need those classifications today. So these are the things we're really ultimately trying to prove continuous, but if that fails, then we're going to default to these other 3 and pick one of those. Okay, so it's a 3-step process. It is a formal proof. So we're using, formal function notation, and we're writing out statements for conclusions. Okay, I'm not just looking for like some chicken scratch work, looking for like this whole thought process. All right, so step 1 is to evaluate the function. So they're giving you this x equals 2. We want to evaluate the function. Okay, so evaluate means to plug it in to find out what it actually equals. If this were on a graph, that would be where we were looking for the closed circle. Okay, so I'm going to plug this in. Okay, I solve this all out. I get 7. This is absolute value. So I'm going to write out the notation here, really formal. I'm using function notation. So f of 2 equals 7. Okay, so that's the first thing that I'm showing for step 1. I'm showing that I can evaluate the function and I get out a number. Okay, step number 2 is now to evaluate the limit. So I'm going to do the limit as x approaches 2, and I know you like it better when I write out the function. We're going to do the limit here. Okay, so in this instance, algebraically evaluating this limit is going to look like the same exact work that I did for step 1. And you're not wrong, because we use direct substitution. But remember, we're formally showing everything, so that's why we're writing it all out. Okay, so limit as x approaches 2 for this function, I am going to write f of x this time, equals 7. Okay. Step 3 is your conclusion. So you can only prove that this is continuous. And remember, it's continuity just at this one value. It's not talking about the graph as a whole. Okay? So you can only prove that it's continuous at this one value if step 1 and step 2 both produce an answer and they're the same answer. So the fact that we have f of 2 equals 7 and the limit as x approaches 2 equals 7, that proves continuity of the graph. Okay, so we're going to say f of x is continuous at x equals 2, and we're going to give a reason. Because f of 2 equals the limit as x approaches 2. That's the definition of being continuous. That evaluating the function and doing the limit give you the same answer. So this was best case scenario. Step 1 and step 2 have an answer. They're the same answer. Therefore, my conclusion, it's continuous at this point. That was best case scenario. Never going to happen again. I'm going to show you an example of removable, infinite, and jump. Okay. All right, so my next function here, I wrote over it a little bit. This is 2x on the top and x squared minus 1 on the bottom. Okay, and we want to show that it's continuous at x equals 1. Okay, so step 1 is to evaluate the function. So we're going to plug in f of 1. Now I want to make a note here. Whenever you have like a rational function or something that can be factored and simplified, when you do step 1, you want to use the very original untouched function, meaning do not factor in order to complete step 1. Okay, the reason for that, if you were to factor and cancel something out and evaluate after, you potentially could be evaluating the function at a whole, and you would get out an answer, which we know is not really true. Evaluating the function, if that were a whole, like let's just say, for instance, that 1 was a whole of this function, you shouldn't be able to get out an answer. You should get out undefined because nothing exists at the whole. If you were to cancel and then plug it in, you're actually finding the ordered pair of the whole, which is different from evaluating. Okay, because if you look at the graph, you don't take the value of the open hole, you take the value of the closed circle. So that's why we're not factoring, we're not canceling, we're using this very original function. Okay, so we're going to plug it in. I get 2 over 0, which is undefined. Okay, so that's good. If something is meant to be undefined when you're evaluating, you want it to come out that way. So for mole, we're going to say f of 1 equals undefined. Okay, step 2 is now do the limit. When you find the limit, you're going to factor and cancel and do all of that. Okay, so I could factor this. On the bottom, I have difference of squares. But this is not actually going to simplify or cancel or do anything. So is it really necessary that I use the factored form? No, you could go back to the original since nothing changed. All right, but we're going to use direct substitution and we're going to evaluate the limit. So algebraically, I have undefined, but remember, I'm solving for a limit right now. So what is my final answer for my limit? If algebraically it's undefined. Alyssa?
Danny.
Good. Does not exist. Okay, so this is a different situation than number 1. Number 1, I had an answer for both part 1 and part 2. Now I have undefined and I have does not exist. Well, I can't show that this is continuous because continuous says they have to equal the same value. And even though they both don't work, that doesn't qualify as being the same value. Okay, so my conclusion here it's not continuous. And I have to give a reason as to why it's not continuous. What did I just show that proved it wasn't continuous? Well, I just showed that f of 1 was undefined and the limit did not exist. So how could they equal each other? Was it 1? Is it 2? I wrote the wrong thing here. Okay, so it's not continuous because f of 1 was undefined and the limit did not exist. Therefore, they can't be equal to each other. Well, now I have to classify it. If it's not continuous, I have to pick one of these other classifications. Removable, infinite, or jump. Well, in order to do that, I have to know what's happening to this function at x equals 1. So what's happening at x equals 1? So look back to our original function, maybe even the factored form that we had in the limit. What is happening at x equals 1? It's not a whole because we didn't cancel anything. So what could be happening at x equals 1?
It can't be infinite, right?
Can't be what?
Infinity?
It is infinite. So, yeah, so at x equals 1, so there's 2 vertical asymptotes here. At 1 and -1, there's vertical asymptotes. And 1 in particular is the value that the question is asking us about. It says at x equals 1. So what's happening at x equals 1? A vertical asymptote. So I classify that as infinite discontinuity.
So it's like when we were doing the domain and range?
Yeah, it's very similar to that. Okay, so this was an infinite example. And when that happened, part 1 was undefined and part 2 did not exist. Okay, so if you kind of remember that setup, undefined and does not exist, both of those, you get an infinite discontinuity. Okay. Let's look at another type. So I'm going to change one of the functions that I had here on my actual demo. Okay, so for my third example, my function is going to be x plus 2 over x squared minus 3x minus 10. Okay, so this is my function, and I want to know if it's continuous at x equals -2. Sorry. All right, so step 1 is to evaluate. So remember, we're using the original unsimplified, unfactored version here. I'm going to plug in -2. Okay, and I get 0 over 0. So it's okay to have 0 over 0 because I'm not doing a limit right now. It's only when you evaluate a limit that this is unacceptable. But I'm evaluating a function. So this is undefined. So we're not off to a good start here. So obviously, this is not going to be continuous. I already can tell that it's not going to be continuous because I didn't get a value here. But I have to continue and figure out what's happening with the limit to then make a conclusion. Okay? So f of -2 is undefined. Let's see what's happening with the limit. Okay, so for the limit, remember, we're going to factor and cancel. All right, so x plus 2 on the top. So I'm going to get x minus 5, x plus 2 on the bottom. So I see that this is going to be able to simplify. I'm going to cross out the x plus 2's. What did I do in crossing out x plus 2? What did I do to this function?
Create a hole.
I made a hole. There's a hole at -2. Ah, would you look at that? -2 is the limit that I'm trying to evaluate. Remember, the limit can equal the hole. Okay, so I'm going to use my direct substitution here. 1 over, I'm going to plug in -2. I got a value. So this has a limit. So this is the reason right here of why I don't want you factoring and canceling until step 2. Because if you factored and canceled and then plugged this in to step 1, you would have gotten out a value. And that would not have been true because on the graph, there would have been an open circle there. And you need a closed circle to evaluate. Okay, so the limit here is -1/7. All right, so now I have an undefined, but this has a value. I already know that it's not continuous, okay, because it can't be continuous if these are not going to be equal. Okay, so I'm going to start my conclusion. So f of x is not continuous at -2 because, so what's my reason? Why is this not continuous?
Because of the function.
Because of the function?
Yeah, like when you solve, like when you solve 2.
Yeah, because of the function, because what about the hole, Dante says. So it's not continuous because f of -2 is undefined and cannot be equal to the limit. which actually had a value because there's a hole there. So Dante, how do you classify a function that has a hole in it?
I don't know, is it jump or whatever?
No.
Or removable?
Removable. So this classification is part of your conclusion. So you need all of this. You need that it's not continuous and why, and then you need this additional classification.
If it's continuous, is it always going to equal, like, so steps 1 and 2 are both going to equal each other, right?
Correct. Okay, so this is what a removable will look like. The function will not be defined, but the limit will. Whereas infinite, neither one of them were defined. So what's the last thing I have to hit now? I did all the other ones except what?
Jump.
I didn't do jump. And what kind of function comes from jump? What kind of function gives a jump disk? Piecewise. Beautiful. Here's piecewise function. Okay. When we do step 1 for a piecewise, doing f of 6, okay, we have to use the piece of function that actually says it's equal to. So I'm going to zoom in here on the function for just a second. So which piece here indicates that it's actually equal to 6?
The bottom one?
Yeah, the bottom one. Look, it says less than or equal to 6. So for step 1, when I go to evaluate the function for piecewise, I'm using the one that says equal to. Only one of them is actually going to be equal to, because otherwise it's not a function. Okay. So I'm using x minus 1 to do this part. Okay, so f of 6 equals 5. To do the limit for piecewise, you have to use both equations because one of them is the limit from the left and the other one is the limit from the right. So the one that says less than is going to be the limit from the left. So x minus 1 would be the equation we use to come in from the left. The greater than is going to be the limit from the right. So the one that says greater is 2x. So we can evaluate this algebraically. We just had to make sure we were paying attention that this is actually two-sided here, and we have to physically do that both. Okay? So the limit from the left, 6 minus 1 is 5. And then the limit from the right, 2 times 6 is 12. So overall then, what's the limit? Because these were limit from the left, limit from the right. What's the two-sided limit? Or the full limit here?
Danny.
Does not exist. How come?
because they're not equal to each other?
Yeah. Each side is not equal. They're coming to a different value. You can't have a two-sided limit. If one side goes to 5 and the other side goes to 12, they're not meeting up. Okay, well, this is different situation for us. Step 1 existed with an answer, and step 2 does not. So we had hope here in step 1 that this was going to be continuous because we got an answer. But then in step 2, all of our hopes were questioned because this does not exist. Okay, so we're going to make a conclusion now. So we know that it's not going to be continuous. We want to know why. So why is it not continuous? Because f of 6, oh, go ahead. Somebody going to tell me?
Oh yeah, I was gonna say because the left and right limit don't equal each other. Like
Right, so it's overall because the limit does not exist. So f of 6 cannot equal the limit. That's really what we're trying to show. That's what we needed. And this didn't happen because, so let's see, not continuous because f of 6 does not equal the limit because the limit does not exist. So how could it? How could they equal each other if one part doesn't exist? Okay, so then what is happening here to make it not continuous? Well, it wasn't a whole because I didn't cancel anything out. Doesn't appear to be an asymptote because I don't even have a rational function. So what is this discontinuity?
Is it because it's not two-sided? It's not a two-sided limit? Like they're asking for a two-sided limit and it's not that?
Right, so that's what this says. But now, because it's not continuous, we have to classify, well, what is it? If it's not continuous, what is it then?
It's a jump.
Good. It's a jump. Okay, so you got one example of each situation. You got a continuous, an infinite, a removable, and now a jump. Now, that's not to say for a piecewise function, it's not always going to be jump. Some of these will be continuous. Like you'll get an answer here, and then you'll get the same thing here. And that'll make it continuous. It just depends on the two functions that you're working with and at what value it's asking for the continuity. Okay, but go ahead.
For a piecewise function, can it only be continuous and jump? It can't be like infinite.
Yeah, you're typically not gonna get like a removable or an infinite in a piecewise function. Okay. All right. So in addition to hopefully getting this screencast posted, I'm gonna post a hard copy of these notes as well. All right. So hopefully, yes.
Are there like rules for like some of the stuff? So like if it's like infinite, are both of the 1 and 2 steps going to be undefined, or like is that just like?
Yeah, that's typically what's going to happen.
And then like if for like
for like removable, if it's like removable, the first one will be undefined, but then this will have a value.
Okay.
Yeah. You're on the right track with thinking like that. All right, my computer is starting to really lag. Oh, geez. All right. I'm just getting your classwork. It's 6 problems. Hang on, I'm just saving. There we go. Okay, so it's 6 problems. Just note that number 5, it's asking you to do 3 separate proofs. It says x equals -4, x equals -1, and x equals 0. They're all just using the same function. But so it's basically 3 separate problems. You just use the same equation each time. All right, so that's your only homework for today because this was our last limit lesson. Tomorrow we're going to review, so you don't have a video or anything today. So go ahead and get started on these. I want you to try and do at least like 1 or 2. We got about 20 minutes, okay? I want you to try and do at least a couple before you leave so that we make sure you understand the process and the setup for the proof, okay? I'm going to get the screencast finished and go ahead, Alyssa, you got a question?
Yeah, for what we did yesterday with the, hold up, I gotta get to it because I don't know like the exact word for it, but it's like when we were doing the, when we like factored it and then we found the whole.
Yep.
Now let's say when you like, if let's say, I don't know how to word this, like, if let's say you don't have a limit after you factor, but you have a whole, like can that happen?
So after I factor it, the limit does not exist, but there was a whole? Is that what you're asking?
Yeah, that can't happen, right?
So I think it just depends on what the value of the whole is and if it matches the value of the limit that you're being asked to find.
Okay, so if it doesn't match, then okay.
Right, yeah. So if they're not the same, then I guess it doesn't really matter that there's a whole, you know?
Yeah.
Okay.
Okay, got it. Thank you.
Mm-hmm.